right, I think we're actually going to end up taking today's topic and splitting it into 2 days. We might take that second piece and merge it with our particle motion next class, or just take an extra day. We'll kind of see how things go. But today we're talking about our first and second derivative tests and what extrema are. I think we're at like basic. So extrema.
We can skip a few days, but our notes are online now.
Our days are all weird because we threw in an extra day with test corrections. And then there's PSAT day that you guys didn't have class, so we didn't have like a day there. And plus it was day 5 and day 6. I don't know about that. Alright, so today we're going to talk about extrema, both relative and if we get to an absolute. We might have to save absolute for next class. And then with that, first and second derivative tests. So again, first and second derivative tests. And again, I think today's topic is pretty neat because it allows you to see some connections between what the derivative, so it's not just that your derivative tells you the slope of your graph, but we can actually pull even more information from that. From our first derivative, we can actually know when my function's increasing, when it's decreasing, when there's a maximum, when there's a minimum. For my second derivative, I can know when my original function is concave up, concave down, when it changes in concavity. There's actually a lot of information you can pull about your original graph just by looking at your first and second derivatives. So that's what we're going to be focusing on today, and if we have time, we'll get to the absolute extrema. But if not, we'll just save that for next class. All right. I can re-orient this real quick. So our first and second derivative tests tell us something about my original function. It tells me characteristics about my original function. All right, so let's start off with our first derivative test. So our first derivative test deals with the first derivative. Alright, and this allows me, it is used to identify multiple things about my original function. Identify the following about the original function. Okay, so using my first derivative, I can know when my original function is increasing. I can also know when my original function is decreasing. And so we'll actually talk about intervals of when it's increasing, when it's decreasing. It also lets us know or identify our local maxes and mins. So local or relative maximum, and same thing, local or relative minimums. We're going to make that plural because we can't have one here. And it also lets us identify something called critical values or critical points. Critical points or values, you'll hear referred to both ways. We'll talk about what this is in just a moment. Okay, so again, by using our first order test and that with that number line, we can find out a lot of information about my original function. Because as we see, sometimes we get functions where we don't know, we can't visualize what that graph looks like. This can help us kind of identify information about it. Alright, so let's kind of talk about a few things. What is a local or relative maximum? What does that mean, local or relative maximum?
Yeah.
It's like on a graph with a bunch of curves, the one that you can see, like not the arrow, that's the highest point.
Yeah, so it's not necessarily absolute, but it is a high point on the graph in relation to its neighborhood, if you would. The area around it, the graph around it, is the highest point within it. So Sandra was saying it's kind of like our hilltops on a graph if we have a bunch of curves. And then similarly, local relative minimums is kind of like the valleys, the low parts on the graph. Can I have more than one area or more than one spot at which the maximum occurs? Yeah, because we can have, again, the local and relative maximums are various height points along the graph. You could have the same, you could have it reach the same height at different spots. How do you think this compares to the absolute maximum? Yeah. An absolute, you could have a local that ends up being your absolute maximum or minimum. Yeah, what is then the difference between an absolute max? The highest of the entire graph, okay? So local is, it's the highest kind of in its little neighborhood, its little area. Absolute is highest in the entire graph. So when we're dealing with absolute maximums, typically we're dealing with a closed interval. It's not often that we're dealing with an open interval, meaning all real numbers. But like we could talk about our absolute maximum. Like for example, the graph y sine x. What is my absolute maximum? 1. And those end up being actually relative maximums as well, all those little items. Right, so same idea with minimums, just the low points. Does anyone happen to know what critical points or values are? Go ahead.
Well, all I know is that it's when you do the first order test and you're solving for x.
You are solving for x in a particular situation. So critical points or values, these are potential maxes and mins. Okay, so go ahead and write that in. These are potential or possible.
I usually test them.
And we do have to test them to find out if they actually are.
Like you do like the above the number line, below the number line, something like that.
Yeah, yep, deals with the number line. So potential or possible maxes and mins. And when I say max and mins, I mean relative maxes and mins. Okay, so again, as Bill was saying, these are potential ones, so we do have to test to see are they actually a max or a min. Okay, I'm just going to go straight into this picture here. So we're going to draw kind of a crazy graph. Let's see, let's go with something like this. 0, x sub 1, x sub 2, x sub 3. I can redraw this one, or more distinct. And this guy x sub 4. Alright, so let's say we have this crazy graph with x sub 0 for x sub 4. A lot's happening here. And from here, we're going to identify our local maxes and mins and some interesting characteristics about those. Okay, so this is my original graph. I'll just put that so we know it's our original. They love to sometimes give you the original, sometimes they give you the derivative graph, so it's really important you keep in mind which piece you're working with. Okay, so let's start off by identifying where our local maxes and mins are. So let's start with local mins. Now, you do want to be careful on assessments as well as the AP exam, because sometimes we'll ask you where does the minimum occur, or where does the maximum occur, and sometimes ask you for the actual minimum or maximum. So when it asks you for where it occurs, we're going to be giving the x values, right? That tells me where on my graph that maximum occurs. If it asks for the actual maximum, that means you need to give the y value at that point, and you know what the actual height of the graph is. So again, maximum and minimum, that's the height of the graph, that's the y value on the graph, but a lot of times we're interested in where that occurs, the x value. So just be careful as to what they're asking for. Alright, so our local mins occur at which x values? What is my first min that I see? Where does that occur? x sub 1. I agree. Next, we have it occurs at x sub 1. Any others?
X sub 3.
Yeah, x sub 3. Any others? Nope, not for this graph. And again, we can see that these are going to be local or relative. So if you look at the neighborhood or the area around it, it is the lowest point, the lowest value in relation to that little area around it. For this graph, do I have an absolute minimum? Why not? Not necessarily because they're the same. What does that mean? Yeah, it's going down forever. So that means there's no single value that is lower than the rest of that. Okay. So my local bins for this graph are occurring at x sub 1 and x sub 3. Okay, now again, we said that the derivative tells us a lot about our original graph. So let's kind of pull in the derivative. What is my derivative at x sub 1? And what is my derivative at x sub 3? So take a look at x sub 1. Remember, your derivative is slope of the tangent line. What is my derivative at x sub 1? Undefined. Why? Cusp. It's cusp. So remember, vertical tangent looks like. So we have a cusp here. This good. So my derivative at x sub 1 is undefined. And our reason is because it's a cusp. You don't have to say that unless they ask you to justify why. In which case we'd say the derivative from the left is an equal derivative. But just for your own purposes, as you're looking back at your question, like, why was that undefined? Oh, because it's cusp. All right, what's my derivative at x sub 3? 0. By drawing my tangent line here, my slope is 0. Okay, that's good to keep in mind. All right, let's actually pause with our local bins. We're going to write more underneath here. We're going to investigate it more. But let's go and take a look now at our local maxes. So again, we're going to talk more about this information with our mins. But let's take a look at our local maxes. Where on my graph do my local maxes occur? Good, x sub 0. We have a high point there. Where else? Good, x sub 2. And x sub 4. Good. So again, these are kind of our hilltops, the high points in relation to the graph around it. It is the highest point in that area. Okay, now again, let's identify the derivative of each of these. So my derivative at x naught, my derivative at x 2, my derivative at x 4. All right, what is my derivative at x sub 0? Yeah, if I look, my tangent line is a horizontal tangent line, the slope is 0. What is my derivative at x sub 2? 0. Again, same thing, horizontal tangent line. What's my derivative at x sub 4? Undefined, good, you can see that. I was attempting to do a cuspy cornery looking thing there. Good, so here we have our derivatives undefined. It's a function value, so it's undefined, limits do not exist. Okay, and again, it's corner, cusp, either one. Okay, so what we can see here is that these critical points, or these maxes and mins, occurred when? What is true about my derivative in relation to my maxes and mins? What is my derivative at all my maxes and mins? undefined or 0. So when my derivative is undefined or 0, then we have those maxes and mins. Now, just because it's undefined or 0 doesn't automatically mean it's a max or min, but if it is a max or min, then that means your derivative was 0 or undefined. All right, so keep that in mind. We'll kind of summarize this all together. All right, so again, critical points, critical values are potential maxes and mins. So something else we could say is our critical points or critical values comes from our derivative being 0 or undefined. All right, that one really went up on a slant, didn't it? Okay, so now let's take a look at what the derivative is coming from the left and the right of each of these. All right, so let's start off with our mins over here. As I do my derivative, or as I take a look at my derivative, so let's phrase it this way. So let's first come from the left of each of my mins. We're going to come from the left on either side. All right, so as x approaches, as x approaches my mins, so x sub 1 and x sub 3. And let's start off by from the left. We're going to take a look at what my derivative is. So we're going to fill that in. And then let's take a look at it from the right. So also as x approaches my mins again, so x sub 1 and x sub 3 from the right. Let's take a look at my derivative. Okay, so again, we're coming from the left side of my min, what's happening with my derivative, and then we'll come from the right side of my min. Alright. So let's start off with coming from the left. So looking at my min, as I look at my little tangents, my little slopes, what can I say is true about all of those slopes? They're negative. Right? Do we agree that all those slopes coming closer are negative? So as I come from the left of my min, my derivative is negative. Or, better way to put it, less than 0. So let's check that on our other min. If I look at my little slopes, my little tangent lines, would you agree my derivative is still negative? So let's see if this changes from the right side. So as I come from the right side, all my little tangents, all my slopes are what? Positive. And again, this should be the same thing over here. All my little slopes, all my tangents are positive. Do we agree with that? Do we see what's happening here? Now, if we stop and think about that, that makes sense. That if I start off with a negative slope, now from your perspective, is this a negative slope? Okay, good. All right, so if we start with a negative slope and then we switch to a positive slope, would you agree that that's a low point in the graph? That has to kind of turn low there. Okay. How do you think this is going to change for maxes? It's going to flip-flop it. So if we take a look at our maxes, coming from the left, positives, positives, still positive slopes, right? So if we do the same thing, but with my maximums, we have it flip-flops. So let's go and write that. As x approaches, x sub 0, x sub 2, x sub 4, from the left, my derivative, we said, is positive. Which, again, seems to make sense. Alright, and then as we come from the right, as x approaches those values, x sub 2 and x sub 4, from the right, work my derivative back. Alright, so as we come from the right side of each of these maxes, what type of slopes are we having? Oh, that one's just the same all the way here. What type of slopes do we have? Negative. And so again, this seems to make sense because if I have a negative slope that then turns to a positive slope, that's going to be a low point in my graph. That's going to be a minimum. If I have the reversal of it, a positive slope, and then it turns to a negative slope, that's going to be a high point on my graph. That's going to be a maximum. Okay. So it's not just enough for my derivative to equal 0 be undefined, but we also need to know what's happening with my derivative from the left. Now, if we stop and think about it, when my derivative is 0, that's going to be any time that it flattens the path, right? Like we see here. Or the undefined, some type of corner or cusp thing. But again, be careful, just because it's 0 doesn't mean that it's going to be a maximum. We'll take a look at why that might be the case.
So the first one is to 0 in that expression.
I'm sorry, what did you say?
So the first order test is 0, right?
First order test is when you take the first derivative set equals 0.
I'm wondering if I couldn't remember.
Alright, questions on what we've kind of discovered here. Now, again, this is really important to know whether we're switching from negative to positive to negative. And I literally will go, okay, positive, negative, or like, you know, looks like I'm doing the wave or something here. That helps you out, by all means do it. Just don't do too many hand motions during test. Do it a little bit in front of you. Alright, if you start doing this, though, I know you're just messing around. Okay, so let's kind of summarize what all this means for us. Ooh. Yes, we'll summarize and we're going to come back and say something. Alright, so in relation to our first derivative test, we know the following. F of x has a relative or local. Relative / local maximum. Let's start off with minimum, since that's what we started off with. It's a local minimum. Has a local minimums. Has local minimums. Has a local minimum. When our derivative, so when f prime of x, and again, think minimum, what has to happen with my derivative? What does it change from? Okay, negative to positive. Alright, so when f prime of x changes from negative to positive. From negative to positive. Okay, so we can pull information about our local min of our original graph by looking at the derivative. Alright, and then similarly we can talk about our maximum. So f of x has a relative or local maximum when f prime of x. And again, think about what a maximum is. What does my derivative need to change from? Good, from positive to negative. When my derivative changes from positive to negative. From positive to negative. Okay. And again, that tells us about our local maximums. Now, these are also the justifications we have to use because AP exam loves to make you write stuff. So when it asks you to justify, this is actually the reason why. You could say f of x is a local maximum at x equal to -3 because f prime of x changes from positive to negative. So this is actually our justification drawing out for it. Now, AP exam is very picky, and thus I will be very picky. We cannot abbreviate as much as we are tempted to. And I apologize for any time that I do abbreviate, and if the keys are abbreviated. For you yourself, feel free to abbreviate, but anytime it is an assessment, we have to write out minimum, we have to write out maximum, we have to write out the words negative and positive. You can't just say plus and minus. You can't say positive. They specifically refer to those examples. We have to write it all out.
Wait, so when we're doing our work though, can we just like that?
For your work, you can do positive. When you go to do your justification, you have to actually write out first. Does that make sense? Like on the number line, you don't write out positive. Okay, questions so far? Okay, so those are two things that we pulled. We also talked about critical values. So let's go ahead and kind of bring the big thing with critical values together. All right, f of x has critical values or critical points. Again, you'll see it referred to either way. Has critical values or critical points, and remember this is possible maxes and mins, possible relative maxes and mins. In case you forget what those are. Alright, so it has critical values and points when f prime of x equals 0 or f prime of x is undefined. Now, they might ask you for the critical values, in which case you don't actually have to test if they're maxes or mins. More likely, they're going to ask you where the maxes and mins occur. Okay, so again, we set it equal to 0 or undefined to find all possible maxes and mins. Those are critical values, and we test it, and I'm going to attach them. It's kind of like when you did your rational root test. The like p over q, the factors of p over factors of q, those were potential factors of your polynomial. Then you had to test it with synthetic division to find out which ones actually. Alright. So we've got these three things. Now it actually also tells us about increasing and decreasing. So let's take a look back at our graph here. And this is something you maybe have already recognized, but so let's just start from the left side of my graph here. My slope all along here, would we agree that that is a positive slope? Is my function increasing or decreasing? Increasing. Okay. And then we've got, okay, it's now negative slope. So and then do we have a positive slope here? And would you guys agree this is increasing? Interesting. And over here, positive slopes. Would you agree that that is also increasing? Okay. So we also have the conclusion that f of x is increasing f of x is increasing when my derivative, when f prime of x is positive, so greater than 0. Okay, so when ask for intervals of increasing, again, you're going to find all this with doing stuff for your max and mins and your number line test. If you got your intervals positive, that means it's increasing. And then let's take a look at decreasing. My original function is decreasing. When, can you guess what the derivative is going to be? Less than 0, negative. So again, if we take a look at our graph here, we're decreasing, we're sliding down the hill. It's a negative slope. Again, we're going sledding because we're going to get 20 days off of school this year. We have a negative slope. And this is the steepest hill you've ever sledded down before. Is sledded a word? Sled down before? Slid down before? Also a negative slope. Okay, questions with that? Okay, so again, what we actually have here are 5 different things we can know about our original function solely based upon our derivative, the first derivative. And they love to ask you characteristics about your graph using this information. Alright, so again, we have local max, we have local min. We have critical values, we have increasing, and we have decreasing. Now, what we did is we had the graph, we were pull information from it. But what if we don't have the graph? How can I actually know when it's a max or min? How can I know when it's changing from positive, negative, or negative to positive? Well, what allows us to kind of organize our information with this is a number line test. And number line tests are recognized by AP. It is a tool to actually use to identify where your maxes and mins occur. So we're actually going to use a number line test to help us achieve this information. Okay, so let's just go ahead and do an example in which we can go use that number line test. Alright, so let's say we have a pretty basic function here. F of x is equal to 5x squared plus 4x. I mean, heck, we could actually factor this and graph it and know what the graph is going to look like. But maybe it gets crazier. But let's just start off with the pretty basic one. Our function is f of x equals 5x squared plus 4x. Find where all local extrema occurs. And then we're also going to find intervals of increase and decrease. Find where f of x is increasing and decreasing. Okay, so find where all local extrema occur. We have a plural, so we're going to go. And also find where our original function is increasing or decreasing. Now, local extrema, all local extrema, that's just the generic category for finding your relative maxes and mins, okay? Rather than saying, find where all your relative maxes and where all of your relative mins occur, we just sum it up in just all local extrema. Okay, so it just means your maxes and mins. Okay, so the first thing we need to do is identify those critical values. Identify those possible maxes and mins, and that's when my derivative is equal to 0 or undefined. So we need our derivative. What is my derivative of this function? 10x plus 4. And so our critical values, those possible maxes and mins, this is where my derivative equals 0. And also where my derivative is undefined. So let's start off with my derivative equals 0. So that would be when 10x plus 4 equals 0. And what do we get for x value for that? Good, -2/5. There's only one possible point from this chunk here at which it could change from maximum. Also, notice, guys, that my maxes and mins is where it changes from increasing to decreasing, or decreasing to increasing, every way you can think of it. Alright, can my function here ever be undefined? No. Now, I don't want to just neglect it altogether because we are going to get functions where you do need to check the undefined, and if I want us to get into the habit now of checking for it. But it doesn't apply for this particular problem. So we only have one potential max or min. So this right here is my critical point. You're not required to label this on the test, just so we know what that is. And again, that's a possible max or min. But we need to know, is it changing from positive, negative, positive, or does it not change? Okay, so this is where we use our number line test. We're going to plug it into my derivative because we want to know, is my slope positive or negative? We want to know, is my derivative positive or negative? Alright, so we're doing a number line for f prime of x, and we're investigating, for this one, we're only investigating -2/5, because that's our only potential max or min. And it is extremely important that you label your number line. Make sure you label that number line. We need to know what it is that you're checking. Are you checking with your derivative, or are you checking with your second derivative, your original function? So you must label that number. Alright. Now, we know for it to be a max or min, we just care is it changing from negative to positive or positive to negative. We don't care what the numbers actually are, what the slopes actually are, just if it's a positive or negative slope. And we know that if it's a max or min, that it's going to be positive leading up to it or negative leading up to it. So we just have to pick a number to the left of this. So number to the left, -2/5, -1. Yeah? Okay. Now again, I'm checking this with my first derivative. So I'm putting it into my first derivative. I want to know if my slope is positive or negative. So I'm just going to check -1. If I take -1 and put it in, do I get positive or negative? Negative. Great. And again, here we know that the slope is 0. How about to the right of it? Let's pick something to the right. You might choose 1. I'm going to choose 0. Make life even easier. If I take 0 and put it in, do I get positive or negative? Positive. So what this number line tells me is that what's happening is all the way up until -2/5, I have a negative slope. Then I have a 0 slope. Then I have a positive slope. So what am I going to have here? A min. So negative to positive, this ends up being a min. Now I can also tell more about my graph as well. If this is negative, what do I know about my original graph? Is that going to be increasing or decreasing? If my slope is negative. Decreasing, it's going down. So I know that my original function is going to be decreasing. And if my slope is positive, what's my original function? Increasing. So from all this information, we can already answer everything about our question here. All right. So we know that's our min. We've got to actually go ahead and formally state this here. All right, so f of x has a relative or local, it's probably a shorter word, minimum at x equal to -2/5. Because, or since, something like that, I'm going to write since so that you guys aren't tempted to write b/c. That's b divided by c, not because. So f of x has a relative minimum at x equal to -2/5. Since f prime of x changes from, what did my derivative change from? Negative, positive, or positive, negative? Now, just look at our number line here. Changes from negative to positive at x equal to -2/5. Okay, so at that point there's minimum because it's changing negative to positive. Now, did we have any maximums? No, let's just go ahead and say there are no maxes so that they know we checked for it, not just that we completely forgot about it. F of x has no maximums. Alright, and then the other thing they asked for was when is it increasing, when is it decreasing? Alright, I'm going to start over here. F of x is decreasing. What is the interval for which it is decreasing? Negative -2/5. Do I include the -2/5?
No.
We're not going to. This is actually something that's debated in the calculus world. Do you include them? Do you not? AP exam says we don't care. What we're going to do is just leave it always as parentheses. I like to take the viewpoint that is neither increasing nor decreasing at that point, so that's kind of the change in interval. But if you put a bracket, it's fine. That's constant, yeah. Okay, so it's decreasing on this interval. How did we know it was decreasing there? Yes, my first derivative was negative. So it's decreasing there since f prime of x is negative or less than 0. And then similarly with my increasing, f of x is increasing on -2/5 to positive infinity, since f prime of x was positive there. It's a lot of work, a lot of words, that's just the nature. Questions on that?
So is everything that's written down in red, is that
Yes, but you do have to have the work to support it. They are looking that you have found those critical values. They are looking for that number line, and then they're looking for this. Yeah, and so this is literally the words you'll write for your AP test. Now, you could change this up. You could say f of x, or f prime of x changes from negative positive at x equals -2 this, so f of x has a relative min there. But as long as you have the piece, where is the relative min occurring, and why do you know that?
so this would only be like your response for this question?
Yes. Multiple choice, they would not have all these words, they would probably just list the maxes and mins. Alright, other questions with this? Now, we're not always going to have that it alternates nicely. Sometimes it does not alternate. Can you guys think of an instance in which we might have? So, for our number line, what if I had that it went from positive to positive, but yet my slope here was 0? Does anyone know what that graph would look like where my slope stayed positive the whole time, but I did have a horizontal tangent at some point of 0? Yeah, it's like x cubed. Let's just for simplicity, I'm going to draw it off to the side. If I look here, at this point, my tangent is a horizontal tangent. We do have that slope of 0. But if I look all along here, my slope is positive, and then it continues to be positive. Okay? And so that's why we have to check it on the number line, because if it doesn't change those signs, then it's not actually changing directions, if you would. It's going from increasing to continuing to be increasing, positive slope to positive slope. It has to change that sign, change that direction for it to be increasing. Does that make sense there? Alright. Let's talk about second derivative. Okay. So number line test for concavity. So next let's talk about number line test for concavity. Number line test for concavity. So that number line test we did with our first derivative told us increasing, decreasing maxes and mins. Our number line test for concavity actually uses our second derivative with a number line to help us know when it's concave up, concave down. Okay, so the number line test for concavity, you use f double prime of x, so your second derivative for concavity. And also to identify potential or possible. So again, possible ones, it's not automatically going to be, but possible points of inflection. Or inflection points. Okay, so our first derivative told us increasing, decreasing maxes and mins. My second derivative tells me concavity and inflection points. Let's recall what concavity and inflection points are. So let's just go back to our x cubed graph. F of x equals x cubed. Let's go ahead and draw our pictures. Okay. So this is my x cubed graph. Do you guys remember what concavity is? Concave up, concave down. It has to do with the curvature. So concave up, kind of nice because it has up in it, is when it looks like this. So it could either be the left side, the right side, or the whole thing. But if you were to pour water on top, it'd fill up with water, right? So concave up means it's kind of turned up like that. Concave down means it's down like that. So if you poured water on it, it would just dribble off the sides. Okay. Now, again, we might not have the nice whole U shape there. Might just have a piece of it. But let's go ahead and kind of break down what we have here. For this piece, is this concave up or concave down? Good. So this is concave down. And then for this piece over here, what do we have? This is concave up. So notice it's kind of the right side of that U. If this were finished out, so if you pour water into this piece, it would fill up that chunk there. Pour water on this, it just dribbles off. Kind of like an umbrella, as opposed to a bowl. Okay, so concave down, concave up. Now, what is this weird word, point of inflection or inflection points? What is that? What do we call this? Yeah, very good. It's just simply where it's that change in concavity. So this here is my inflection point, or point of inflection. You might see me abbreviate point of inflection as POI, like sometimes in your instructions, or concave up, concave down like that. Again, though, when we're writing out our justifications, we do have to write out everything. All right, so inflection point, and again, this is a change in concavity. It's not always going to be seen at zero, but it's where it changes in concavity. Changes from concave up to concave down, or vice versa. Okay, so our concavity deals with the second derivative. So let's go ahead and take a look at this problem here, kind of working through that. So let's do our first derivative, 3x squared. From there, we know we can find intervals of increasing, decreasing, possible maxes and mins. Do I have any local maxes or mins here? No, there's no high point relative to everything around it. There's no absolute max, no absolute min. Alright, and we could find intervals of increasing, decreasing, but we're just worried about concavity. So let's do our second derivative, which is 6x. Alright, so again, our second derivative, so this is kind of similar to our first derivative test. We want to go and take a look at when our second derivative is equal to 0. And we also want to take a look at when our second derivative is undefined. This will identify potential points of inflection. And then we have to test it on the number line to see. And again, if we have that, like here we have that horizontal tangent that gives us that slope of 0. Okay, so taking a look at my second derivative equal to 0, that would mean 6x equals 0, which gives me x equals 0. So again, this is a potential or possible POI. We have to actually test it. Can my second derivative ever be undefined for this one? So we don't have to worry about that. Okay. And again, we're going to do a number line test, but now with our second derivative, again, it's extremely important that you label that as your second derivative. Especially when you get to problems where you have to do your original, your first derivative, and your second derivative. It's a lot. And the only one we're testing here is 0. Okay. So my second derivative is what we're plugging into because we're interested in when my second derivative is positive versus negative. So I'm going to take something to the left of 0, so I'm just going to take negative 1. If I take negative 1 and put it in, what do I get? Good. Overall negative. And at 0, we know it is 0. Alright, if I take positive 1 and put it in, what do I get? Overall positive. Because it changes signs, changes from negative, positive, positive, negative, we know this is indeed an actual point of inflection. Okay, so because it changes signs, we know this is a point of inflection. Now, for points of inflection, we don't care whether it's negative, positive, positive, negative, just that it changes signs, because all we're talking about is changing concavity. We don't actually specify a change from concave down to concave up. Okay, so we're talking about this, we just say f double prime of x changes signs, so we know it's a point of inflection. All right, now let's take a look at the relationship between our original function and our second derivative. When my second derivative was negative, what was my original function in terms of concavity? Concave down. So we had my original function was concave down when my second derivative was negative. All right. When my second derivative was positive, what type of concavity did I have? Concave up. So from my second derivative, with the number line test, I can know when my original function is concave down, when it is concave up, and when it is changing a concave down inflection. So for this particular problem, we could say that f of x is concave down on the interval -infinity to 0 because f double prime of x is negative. But let's just kind of summarize what we would do with our second derivative test. Okay. So we're just going to kind of summarize what we have. Yes.
Are we still gonna, if we're doing like, you're gonna really like state problems, but are we still have to state like what we did for the first one test? Like,
Only if they ask for anything about increase and decrease.
same class, we still said there was no maximums, like even though there was like none within the thing. So we still wouldn't have to.
You wouldn't have to hear. Did I actually give you instructions for
No,
this?
you didn't.
No. If the instructions simply said, when it tell me intervals of concavity or inflection points, I said nothing about maxes, mins, increasing, decreasing. You don't have to deal with first derivative only in the sense of this information. Does that make sense? All right. So what we conclude with this, what we have is that f of x is concave down. Now I'm abbreviating it in our actual justification. We would write out concave down. But we have it's concave down when our second derivative is negative. Do we agree with that, with what we just said? Okay. We have my original function is concave up when our second derivative is positive. And then we have a point of inflection. F of x has a point of inflection. So f of x has a point of inflection when f double prime changes signs.
Can we abbreviate CCD and CCD?
Not in our justifications. But I will say oftentimes I feel like they ask more about increasing and decreasing concavity for justifications. But yeah, it's not one of our abbreviations. Alright, so f of x has a point of inflection when my second derivative changes signs. And again, you don't have to specify which way it changes, this is that it changes. So again, we would write out everything, but we've got concavity, so concave up, concave down, and point of inflection. So first derivative test tells me increasing, decreasing, max, min, critical point. Second derivative tells me concave down, concave up, point of inflection.
So we don't have to specify the point at which.
You would, well, your point of inflection you would. You would say f of x has a point of inflection at x equal to whatever.
But you don't need this.
Only if the problem asks for it. Alright guys, your homework says 2-6 and 2-7. We're going to start with just 2-6 tonight since we're kind of breaking up the topics. And again, if you're absent last class and didn't get your quiz back, make sure you come to me here at the end so I can do it for you.